Hello, this is Llamazing, and I'm going to present a new application for the celestial theodolite today. But first, let's recap what it is for those who don't know. The celestial theodolite uses observations of stars setting behind mountain peaks. By noting the exact second where the star was no longer visible, you can then consult an astronomic almanac to determine the uncorrected angle to the star at the time, as in not influenced by refractive and other optical effects. By forming a right triangle at the base of the observed mountain with the other 2 points at the observer and the mountain peak, the geometric angle to the mountain can be easily calculated using basic trigonometry, where the angle is the arctangent of the height of the peak minus the height of the observer for this vertical distance divided by the ground distance, which is also going to be equal to the angle to the star from the almanac. It is interesting that the physical angle to the peak of the mountain comes out the same as the almanac angle to the star, despite there being no allowance for Earth curvature in the calculations. Most of the observations are done at long enough distances away that the amount of ground curvature would be significant. When the calculations are done using globe math, and that accounts for the curvature, the numbers are off by the amount of ground curvature present. Refraction, the bending of light due to the changing density of the atmosphere, has to be invoked to compensate for that difference, bringing it back to where it would be without the curvature. The following celestial theodolite measurements have been made to date, sorted by observation distance. The farthest one done so far has been to North Peak in Colorado, with a distance of 130,000 meters. But instead of discussing stars getting occluded behind mountain peaks today, let's try something new and completely shatter the current longest distance observation, which is going to be 7.7 million meters, which is 60 times the furthest record to date. And here's what we're discussing: solar eclipses. A total solar eclipse occurred on April 8th, 2024 in the United States, with totality lasting from 4:30 p.m. to 8 p.m. UTC time, and that was 4.5 minutes at any one given location. Noteworthy cities along the path are Austin, Texas, Dallas, Texas, Little Rock, Arkansas, Indianapolis, Indiana, Toledo, Ohio, and Rochester, New York. The path was going from the southwest to the northeast. And then, of course, the sun and moon are traveling from the east to the west. And the reason that the eclipse path travels from west to east is because the sun outpaces the moon, swinging the shadow around as it passes. The reason the path of the eclipse travels north is because the sun is getting farther away from the moon, making the angle of the shadow down to the ground more shallow and thus farther reaching. So now we've got to understand the eclipse. Where to begin? First, I want to understand why the path of the eclipse shadow would travel to the north. So the first thing to do is study the movement of the sun and moon in Stellarium, which is a planetarium app showing the position of the stars for a given location and time. Starting at the farthest point for the eclipse shadow, I drew a great circle route to the moon. Then at intervals of 1 nautical mile, which is 1/60th of a degree of longitude, I used Python to calculate the latitude and longitude coordinates for each of those interval points. I also recorded the observer's altitude angle to the sun and moon, which excludes refractive effects. And then I plotted the angle versus ground distance for both the sun and the moon. So starting here with the sun, the first step is to create a linear trend line of the plotted data, which you can see is this dashed blue line. And the R value is high, indicating it's a good match, or close to 1 rather. The slope of the trend line gives rise over run, so the slope value of -9 e to the -6 has units of degrees per meter. Vertical is degrees, and the horizontal is millions of meters. When we take the inverse, 111,000 meters per degree, and then divide by 1852, which gives us 60.038 nautical miles per degree. This is close to the expected 60 nautical miles per degree, where the sun drops by 1 degree for every 1 degree of distance traveled. Going back to this 111,000 meters per degree number, if we multiply by 360 degrees to get the circumference, and then divide by 2 pi, we get the radius value of 6.3 million meters. This is close to the 6371 radius for the Earth value, which is what we'd expect. But now when we go to the moon, something interesting happens. If we generate the trend line like before, this gives us 9.13 e to the negative 6 degrees per meter. We invert to get 109,000, and then when we divide by 1852, we get negative 59.1327 nautical miles per degree. Most unexpected. And then when you continue the math out, that results in a smaller radius value of 6.27 million meters. So putting this into perspective, when starting with the sun directly overhead and traveling 5,400 nautical miles, or 90 degrees longitude, the sun drops down to 0 degrees. For the moon, however, we only have to travel 5,300 nautical miles, which equates to 88.7 degrees longitude for the moon to drop down to 0 degrees. Putting it another way, if we see the sun as if it is traveling along a celestial sphere with the radius of the Earth, then we see the moon traveling along a similarly slightly smaller celestial sphere. And that's what we're showing here with a side view of where the sun and moon appear as the observer increases their ground distance. So the scale is millions of meters, both directions. And with the sun, it's at the 6.3 million meters. The moon's 6.27. And then if we multiply by pi over 2, we get the base radius, which is 10 million meters for the sun and 9.8 million meters for the moon. So now that we have that background out of the way, we can actually analyze the data. And you can see here the path of the center of totality spanning across the US. And the data for the eclipse path is available as a Google Earth KML file from this NASA website. It tells us precisely where the center of the eclipse shadow is cast at a given time. There are 6,770 data points at 1 second intervals spanning from 6 p.m. to 7:45 p.m. for 112 total minutes. Next, the latitude-longitude coordinates for the ground positions of the sun and moon are needed over that time span. I wrote a Python script to extract this information using the AstroPy module. This allows us to calculate the distance along the ground from the observer at the eclipse shadow to both the sun and moon positions, giving us a base distance of our triangle. I also extracted the altitude measured in degrees of the sun and moon above the horizon for the observer, but these are for reference only. They represent an optical position in the sky, and we need to use the true physical position. The final measurement needed is the height of the object doing the occluding, which in this case is the height of the moon. What we're going to do is assume the moon is fixed at the 6.27 million meter height we found earlier, and assume it is only an optical effect that causes the apparent position of the moon to drop in the sky as we get farther and farther away from it. The following table summarizes the known and unknown parameters. So first we have the center of the eclipse shadow, latitude and longitude, which we got from the data file from NASA. Then comes the observer elevation height, where we can take those lat-long coordinates and upload them to gpsvisualizer.com, which will export a CSV with the elevation data. Then the sun and moon ground position, latitude and longitude, which is generated in Python. We have the ground distance from observer to sun and moon, which is calculated using Haversine from those latitude and longitude coordinates. The height of the sun and moon is what we looked at earlier, and we're going to assume a fixed height over the observation period of 112 minutes. There's the observer angle to the sun and moon, which is generated in Python, but we're not going to use it because it is the apparent position. And then finally, the physical occluded angle from observer to sun and moon, which we don't know, but we can solve using basic trigonometry. Our assumptions are as follows. Number one, the sun and moon are at different fixed heights as they travel east to west. We'll consider any change in height negligible over the 112-minute observation window. Number two, assume the physical positions of the sun and moon are in a direct alignment with the position of the observer. That is, drawing a straight line from the observer to the physical location of the sun is going to intersect the physical location of the moon. Third, the light from the sun to the moon, and likewise the shadow from the moon to the observer, is going to follow a straight path, where refractive effects of the light are negligible. Since we're using physical and not optical positions for the sun and moon, optical effects do not apply. And lastly, no corrections are going to be accounted for ground curvature. And here are the objectives of the analysis. Celestial theodolite calculations generally involve calculating the height of the mountain peak using a triangle of the physical geometry and then comparing to the known height in order to evaluate the measure of success. Lacking certain key measurement values forces a different tactic for this analysis. In this case, over 6,000 data points are available to analyze, so instead, success will be measured in regard to consistency across the full dataset. We don't know what the height should be, but can we consistently calculate the same height across all the data points? These 6,000 data points aren't simply a similar measurement taken over and over again. Since the sun and moon are moving in the opposite direction as the eclipse shadow, the distance is constantly increasing from 2.6 million meters to 7.7 million meters, which is an increase by a factor of 3. Likewise, the altitude angle from the observer to moon drastically changes as well, going from 70 degrees down to 19 degrees, a change of 51 degrees. And then the azimuth to the moon sweeps out 140 degrees. The observer latitude changes 30 degrees, and the observer longitude changes 60 degrees. The observer elevation is fairly consistent except for this mountain range over Mexico. So the key parameters vary quite a bit over the data set. Now let's get into the actual analysis. The first step is we're going to assume the height of the moon is fixed at the 6.27 million meters number we found in section 2. H moon equals 6.274 million meters. Step 2, calculate the occlusion angle using a right triangle where the base is equal to the ground distance from the observer to the moon and where the height is the moon height. So the occlusion angle becomes the arctangent of the height of the moon divided by the distance. Step 3, we're going to make another right triangle from the observer to the sun using the same occlusion angle from step 2. And since in a solar eclipse the sun and moon are lined up with each other to cast a shadow on the observer, we can assume the angle from the observer to the moon is the same as the angle from the observer to the sun. So now we're solving for the height of the sun, where our equation is height of the sun equals distance of the sun times tangent of that occlusion angle. And that's all there is to it. So now we just have to perform this calculation for all 6,700 data points and then calculate average and standard deviation values. The average comes out to 6,374,000 meters, which is very close to the 6,371,000 for the Earth radius. And then the standard deviation comes out to 6,200 meters, which is less than 0.1% of the average, which indicates the data is highly consistent. This is showing the height of the sun plotted out for all 6,000 data points, and the result is very flat. This is versus time. We can also show it versus distance. And the key point to consider here is we're actually starting the eclipse here, and the distance gets smaller and then gets bigger, so it's actually going over itself exactly, and it's so perfect you can't see it. So if you're thinking the reason it looks so flat is because the amount of globe curvature at this scale is negligible, then let's take a look. It most definitely is significant, which you can see here is 4 million meters at the end, which would be very significant compared to the 6 million meters of the sun height. And since we didn't have to account for it in the calculations, that is very telling. And then lastly, let's look at the physical angle versus apparent angle. There's a discrepancy between the physical angle that we calculated and the observed angle given by stellarium, even when it does not include refraction corrections. This disparity is shown below, which increases the lower the angle gets, similar to what we saw with the profiles of the celestial sphere. The sun and moon appear to be lower than their true physical position on account of optical influences. Here we can see the physical location of the moon is at 40 degrees, but the apparent is at 20. So there's a pretty big disparity there. And here's a spreadsheet showing the data. You've got the eclipse path, the sun, latitude, longitude, and distance calculations. Same for the moon. And then here's where I calculated the sun height. So you can see there's just a lot of data points here. And then you've got the average and standard deviation. So in conclusion, the relationship between the sun and moon during the total solar eclipse can be modeled out with very basic trigonometry while maintaining good consistency for the duration of the event. It is not necessary to make any corrections for ground curvature, nor to correct for refractive events diverting the path of the sun's light. This study does demonstrate that there is a difference in the physical position of where the sun and moon actually are located versus the apparent position of where we think that we are seeing them due to optical effects. Even the globe model agrees on this point. This raises the question, is the ground beneath our feet curving, or is it the sky that appears to curve due to the nature of how our eyes perceive it, notably with the same radius value at which the Earth supposedly curves? I leave it as an exercise to the viewer to draw their own conclusions, but this only scratches the surface, and there's so much more to explore. And then let's briefly go over some things I have here in the appendix. So if you're wondering about moon height over time, here it is mapped out for 2 months with the eclipse happening here at April 8th. And it is changing by about 10,000 meters over that duration. If we zoom into the period of the actual eclipse, you can see it's going from 535 to 570. So it's less than 40 meters change, so not very significant. And when I plug the numbers in with the varying moon height, the average number for the sun height only decreases by 1 meter, and the standard deviation decreases by 10 meters, so it's not that significant of a change. And then earlier we were talking about the 88.7 degree longitude change for the moon to go directly overhead to drop down to 0 degrees. So here we have an observer directly under the moon at point A, and then at point B is that 88.7 degree longitude difference showing what it would look like on the globe model. And since we have a right triangle here at point B, it's just a matter of taking the cosine of the adjacent divided by the hypotenuse. So you can see the math here, and it comes out to 275 million meters. Now we're told that the moon is 350 to 400 million meters here in this range, and what we're getting falls a bit short. And then lastly, you might be wondering how you could solve this same process on the globe, where you're solving for the sun height. And it's very similar, but you have different triangles. And then in this case, you're actually accounting for the Earth curvature. But the problem occurs when you have any triangle, the sum of its 3 sides has to equal 180 degrees exactly. And so if I assume the minimum distance to the moon of 350 million meters, what happens is this distance to the sun angle and the observer angle, those two alone add up to more than 180 degrees, so it's not possible to make a valid triangle, and it doesn't work. So I hope you enjoyed this presentation. I'm sure there'll be more discussion in the future. Thank you.